So now that we have our labeled data set, we're going to need to train a model that can recognize the brand of a wristwatch given an image of it. Now, in order to train this model, we're going to need a high-performant GPU instance. So you're going to need to use a cloud computer of some sort. You have a couple options here. I prefer to use AWS, just a personal preference. You can use things like GCP or Paperspace. I just find AWS to be simpler, so I'm going to use that. So I'm going to go to EC2 on my AWS console. We're going to go to Instances and Launch Instance. So when you're launching an instance on AWS, you launch it from this thing called an AMI or an Amazon Machine Image. Now they have just like basic Linux and Ubuntu installations and things like that. But if we go to community AMIs, there's actually a whole marketplace and a whole bunch of pre-built images that are like optimized for specific things. So if we filter by this query deep learning, we'll see that they actually have a deep learning Ubuntu AMI that's optimized for training neural networks. So we're going to launch one of those instances. Now, the actual instance type we're going to use, we want to filter by GPU instances because we're going to be training on GPUs. And I'm going to choose p2.xlarge and use this one. Now, one thing to note is that when you're using a GPU instance like p2.xlarge, these are kind of expensive. So this is going to be around 90 cents an hour, I think, to use. So you just need to make sure that when you are using these kind of instances that you turn them off when you're not using them, or you're just going to get charged a bunch. So yeah, so anyway, blah, blah, blah. We don't need to do any of this. Default security groups is all that we need, and then review and launch. So we're going to launch this. It's going to ask us which key pair we want to use. So I have one that I made called Machine Learning Server that I have saved locally. If you don't have one already, just create a new key pair and download it to your computer, and then I'm going to choose Launch Instance. So the instance is now launched. Something else that I want to do is that when you launch an instance on AWS, it's going to assign a IP address to it, and then when you stop the instance, it's going to remove this allocated IP address, and then when you relaunch it, it's going to assign a different IP address. And with these machine learning instances that we're constantly spinning up and then shutting down, I don't want the IP address to keep switching because it's going to get annoying to keep track of. So one of the things you can do is assign a persistent IP with an elastic IP. So if you go to the elastic IPs and just click allocate elastic IP address, it'll assign you a new IP address. So allocate, so it gave us this 52.21.208.157. So I'm going to click on this, and then I'm going to choose associate elastic IP address. So the allocation assigns us a new IP address to our AWS account, and then associating the IP address is going to say, I want this IP address to persist on that instance even when I shut it down. So I'm going to choose the one, and now I don't even remember the name, what instance that was. So now I need to look again. So it's the one that ends in 7.1 is the one that we just spun up. So elastic IPs, the 5.7.1, and we want to associate this with instance 7.1, which is that instance that we just made. So we're going to associate it. And let's go back to our EC2 console. Now we see that this IP address is going to be persistently associated with this image that we just spun up. So let me copy this. And then the next thing that we want to do is we want to actually SSH into that server just to make sure that that all works correctly. So I'm going to do SSH-I, and then this needs to be the path to that PEM file that you created when you launched the instance. So I know that mine is in my desktop /keys/machinelearningserver.pem. And then there's one other thing that we're going to want to do, which is we want to map our local host port 8888 to the cloud instances port 8888. And that's because when we run the Jupyter Notebook dev environment, it's going to be running on port 8888 of the cloud instance, but we want to be able to access it from our local web browser. So I'm going to do that with the command -L, localhost 8888 goes to localhost 8888. And that'll just map the remote port to our local port. And then we need to give the IP address. So Ubuntu @ and then let me copy this IP address real quick. Copy. Yeah, here. So this is all that we need to SSH into our machine learning server. I'm going to say yes to add that host. And then if you're here, now we can see that we're actually in the remote server. So just a couple of housekeeping things before we launch our dev environment. These machine learning servers come pre-installed with Anaconda, which is a Python package manager and virtual environment manager. I'm not super well versed in the Python ecosystem, but I know that a lot of people use Anaconda in production. You don't need to worry too much about it, but you just do need to run conda update conda because this is a fresh new instance just to get the Anaconda package manager to be at the latest version. Cool. And then we're going to run conda install -c PITorch -c FastAI PITorch FastAI. Cool. And now that's done. So we're using this library called FastAI for doing our machine learning. Yeah, it started like just to give like quick context on what that is. So like neural networks are just math, right? They're just matrix multiplication, and they're all described in all these mathematical white papers and stuff like that. There was this library a few years ago built called TensorFlow, which was a Python implementation of neural networks that gave developers like higher level abstractions to do this kind of machine learning with. This was built by Google. It was kind of hard to use. I tried using it a few years ago. But in the last few years, I think there's been this shift away from TensorFlow to this library called PITorch, which was built and maintained by Facebook, which is the same thing. It's like Python implementation of neural networks. But then there's this library called FastAI, which was built on top of PITorch. And this is even higher level abstractions for developers to use to implement neural networks without having to get into like all the nitty gritty details that you'd have to in PITorch. So I think that like TensorFlow has kind of fallen out of favor, and now people are using this FastAI and PITorch. So it's like you can use FastAI if you just want to do something quick and dirty. You can then dip down into PITorch if you want to get into like lower level stuff, and then you can dip into like the raw math if you really, really want to mess around with it. And this is kind of funny, right? Because like the same thing happened with like UI development, where Google built this library called Angular, which was popular for a while, and then Facebook built this library called React, and then everyone was like, yeah, Angular sucks, and we all started using React. So it seems like this kind of like happening again in machine learning, but yeah, that's neither here nor there. But anyway, we just needed to install PITorch and that FastAI library because that's what we're going to be using. Now I'm going to make a new directory called Chrono Analyzer. I'll cd into that, and I'll make another directory called code and another directory called data. Now we need to upload that batch of 4,000 images that we had from our local web scraper onto our server. So let's do that now. So cd into my desktop, and then we'll scp-i. So scp is the command to take local files and send them to a remote directory. We need to give it the pem file, so /keys/machinelearningserver.pem. Yeah, and then we need to give it the path to the local thing. So I made that folder called Chrono Analyzer on my local machine. And in that, we had something called scraper/images. And we want everything in that folder. And we want to send it to Ubuntu at whatever the IP address was, which I forget. It's this. So do Ubuntu at this, and then the path that we want to send it to. So /home/Ubuntu is the root directory, and then /chrono analyzer/data. So we can see that it's now uploading those images of those watches. And if we cd into the data directory here, and we do like an ls, we can see that we're getting those images. So we could do that same command that we ran earlier, ls-la/wc-l, to see the progress. So we have 260, and this is going to be around 4,000 things that we're uploading. So I will wait a minute for that to finish, and then I'll come right back. Okay, so now this is finished, and we see that we have 36 images under this data folder. One more thing that I'm going to do. So these machine learning servers come pre-installed with TMUX. So TMUX, if you've never used it, stands for the terminal multiplexer. And it's just a way to basically use tabs within one terminal window as opposed to having to open multiple terminal windows or like send processes to the background or anything like that. But every TMUX installation has a configuration file. I have one local on my machine. I'm just going to scp that guy up also. So instead of this, I'll do ./.tmux. Or it's here, it's /.tmux.conf, and I'll send that to the root directory, .tmux.conf. Yeah, so now I should be able to do a new TMUX instance with my own keyboard configuration. Yeah, so I think that's all that we need to do in order to launch our instance. So let me cd into Chrono Analyzer, and then let me launch a new TMUX instance with TMUX new session -n-ml. Yeah, and now I can just make tabs in my terminal and switch between them like this. So now in this Chrono Analyzer, I'm going to run the command Jupyter Notebook, which is how we launch the Jupyter Notebook dev environment. Now it's going to launch it locally on this machine, But because of that port forwarding we did when we launched the instance, it should forward this to our localhost 8888 port also. So it'll give us a URL that we can connect to with this token. So I'm going to just copy this gentleman over here, and I'm going to paste it here. Yeah, and you can see that they have the directories that we made of code and data. And I'm going to go click on code. And if you can get this far, you are ready to start building the machine learning model. So now we're ready to build our model. So I'm going to go create a new notebook by doing new, and then you choose the Python environment you want. I want Python 3. You can rename the notebook here. So I'm going to call this Chrono Analyzer Classification Model. And yeah, if you're not familiar with the Python notebook dev environment, it's essentially just like using a console REPL, but it has two main differences, I think. So the first main difference is that you can persist equations across sessions. So if I wrote like 1 + 1 and evaluated it to get the output, well, now this entire notebook is one unit where this 1.1 is, like persisted in the history of it. So I can share this session really easily with somebody else and they can see the input that I gave into it. So that makes it really good for collaborating and like sharing across different people, across different sessions. The other thing that it does, like I think a lot better than a console REPL, is that it can you can plot graphs and like plot images in it very easily too. So we're going to be using like a few tables and images and graphs and things like that. So using this kind of dev environment, I think is just a lot better for it. There are a couple commands that are just like easy to know. I'm not super much an expert in this or anything, but like I know that if you hit B, it makes new lines, and then if you hit DD, it deletes lines. You can hit enter to go like into an individual cell and enter to go like down, and then if you hit shift and enter, it evaluates the line the way like a normal REPL would. So that's pretty much all you really need to know to get started. I'm going to import a couple libraries now just to get started. We're going to be importing a lot more, but I just want to do this to get started. So I'm going to do import pathlib, and then I'm going to, from fastai.vision, import image list. So we're going to make a new path, which we're going to call the chrono images path, and that's going to be equal to pathlib.path, and then the path where our images live. So home Ubuntu /chrono analyzer /data. And if I looked at that chrono images path, you'll see that it's an instance of POSIX path on our file system. And then I'll say data is equal to image list .from folder chrono images path. And if we looked at our data right now, oh, and I spelt this wrong. So it needs to be analyzer.data. And if we look at our data now, we'll see that it's an image list of 3,093 items, and their images like this, 3, 210, 210. So just to take a step back for a second, we can see that we created this thing called an image list where we have a bunch of images that are 3, 210, 210. Now, if you remember, each image in our data set is 210 by 210 pixels. And the reason for this 3, right, is that like each pixel is an RGB value that goes from 0 to 255. So you can think of each image, right, not as an image, but as an array, that each item in the array is a 0 to 255 value of the pixel value at that initial thing, right, 138 and blah, blah, blah. And this goes like 210 by 210. So it's actually a matrix. It's a 2 by 2 array where each item in the matrix is a depth 3 array also. And we're going to have a series of these images here, and we want to write a function that can take those pixel values in, and it can return an array of predictions. And remember that there are 13 brands that we have that we want this model to be able to classify on. So we want to be able to say, given this array of pixel values, take that as input, and then the output will be each brand and a value from 0 to 1 on how confident the model is that the image pixel values represent that brand. So that's really what this function is going to do, right? It's going to take one of these RGB matrices as input, and its output will be an array of predictions based on how confident it is for each brand. Now, in order to actually do that, there's a few manipulations that we're going to need to do before AI data can use this. So the FastAI library is going to be able to build a model like that, given that we can give it something called an image data bunch. And there's a couple things we have to do on our folder of images in order to create this image data bunch correctly. So the first thing we needed to do was create an image list where it knew about the data set that we had and like the format of each image. So doing this image list from folder command took care of that. The next thing that we're going to need to do is partition that image list into two factions, one called training data and one called validation data. And there's no exact science to the amount the like percentages each partition needs to be, but normally you'll see validation data being around 20% of the total data set and training data being around 80% of the whole data set. The idea here is that when we make our model, we want to withhold some percentage of the data from the actual training data we give to the model so that we know as we're training it how good of a job it's doing. So if we have, for example, an image of a watch and we know that it is a Breitling watch, and we train our model, we're going to, as we're training it, periodically give it this image of the watch that we withhold and say, hey, given this watch right here, what would you predict it is? And if it predicts it's Breitling, then we know that the model's doing pretty good because it was able to make an accurate prediction on data that it never saw. If we were not withholding this data and just asking it to predict how good it is based on its training data alone, well, then it would be too easy because it would be just asking it to predict things that it had already seen. So we always want to partition training and validation data. So that's like step one is like that partition. Step two is we need to tell it how to label the data. So it knows about the file path where our images reside, but doesn't actually know where the labels of the data are. In our case, we saved the labels on the file name, but there's a few ways you can do this, right? You can have separate folders where you have the labels for the data and things like that. So we need to let the library know how we're labeling the data. Then we need to do something called transforms, which we'll talk about in a second. And finally, we need to normalize the data. So we need to do all four of these things. What I mean by normalize the data is I said that the data looks kind of like this, right? Where we have pixel values, like RGB values, like 0 to 255. Well, when you're going to actually train the model, you don't want values from 0 to 255 as the pixel values. You want everything in your model to be a value between 0 and 1. And this just is some math reason why you need to have 0 to 1 values, but that's what that whole normalization process is telling it, given the way that your data looks, how do we normalize it? Given like, what do we want the mean to be? What do we want the standard deviation to be? Things like that. In order to like normalize your data to pass into the model, because it just happens to like train better and generalize better when you do it that way. Okay, so the first thing I'm going to do here is I'm going to tell this library how to partition our data between training and validation. And the way I'm going to do it is with this function called split by rand %. And now if we looked at our data, we'll see that we actually have two sets, right? We have training data, which is 3147 items, and validation data, which is 786. And the way that we chose to partition it was just randomly. Now, you could just have separate folders for training data and separate folders for validation data. And that can be good because then you have like a repeatable process where you know what data is in the training set and you know what data is in the validation set. So that's really good to have like to not have randomness in this anywhere so that you can have predictable outcome and you can share it easily. But there is a way to get around that. So I'm going to import the NumPy library, import NumPy as NP. And you can run this function called np.random.seed. And I'll set this to 42, which is just a random number that I chose. So if you set the NumPy random seed, well, that means anywhere that randomness is introduced in any function using just like the Python random library, it's going to have a predictable outcome given that you change the random seed to this. So if I make the np random seed 42, and then I had this exact same data set and I shared it with someone else and they set the random seed to 42, even if we're splitting by a random percentage, we're going to get the exact same outcome. So that's a way to like just split randomly, but still have reproducible outcome. So now that our data is partitioned into training and validation data, we need to tell the FastAI library how we are actually labeling the data and how it knows what the classifications are. So if I look at the way that like this file is labeled, if I look at the file system, so we have something that looks like this, like zenith 64 18500.jpg. And there's this function we can run here that's label from RE, which is to say we want to label by a regular expression on the actual name of the file itself. So I use this site rubular.com to write regular expressions whenever I need like help figuring it out. So you can just give it the test string, and we want to write some regular expression where we can just match this part of the test string. And we'll test it on a couple of different file names just to make sure it works. Yeah, so we know that it's going to be one or more characters followed by a hyphen, and then one or more characters followed by a hyphen, one or more characters followed by a hyphen, and then .jpeg. Oh, sorry, there's no hyphen here. And then we know that we want the match group to be the first thing here. So if we put this in parens, we'll see that we match Zenith out of this. And to give it just like another example, if we scrolled up here and tried like this one, we'll see it matches Seiko out of that. So this looks like a regular expression we could try. So let's go into here and label from regular expression and give it this. And see, like this didn't actually work because it is using the full file path name as the matching class. So we need to just make sure that we get rid of the file path. So we'll say like any file path, any characters, and then a slash, and then this matching string. So if we do this and then did our data, we'll see that now this is not just an image list, it's a label list where it has the training and validation data partitioned, but it knows about the categories. So it knows Gucci, Patek, JLC, Seiko, AP, etc. As the categories. And we just pulled that using a regular expression out of the full file path here. So let's talk about transforms. Now, there's this idea in machine learning called data augmentation, which is a way to like vastly increase the size of your data set from just like a few images. And the way you do that is by taking one single image and transforming it in a bunch of predictable ways to create new images that you know want to be classified the same way. So to explain this, I'm going to look at some images of kittens right here. So this is one image of a kitten right here. That's been transformed in a variety of different ways, such as like reflected over the y-axis and cropped. This has, it's a little bit squashed and it has the brightness taken down. This one is just like slightly tilted or rotated in a weird way. And this one's like mirrored, etc. Right? But all of these are the same image of a kitten. So if you're trying to make something that could like classify between dogs and cats and all you had was this image, well, you could actually predictably get 8 separate images just by doing these simple transforms to it and knowing that they're classified the same way. And that's a really cool, powerful thing because remember, like the input is just that matrix of pixel values. So just by slightly transforming the image, the pixel values are going to be completely different, but you know that they want to be you want to classify it the exact same way. And that's why these libraries like FastAI are really good because doing this kind of data augmentation makes your models significantly better, but it gives you just like really good defaults for, hey, we want to transform our data with just these default set of transforms and like not even worry about it. And it's just going to make our models so much better. So they have this default method called getTransforms, which is just a default set of transforms that you can use. So if we do that and then do .transform with the getTransforms, and then look at our data, it's still a label list, but now it knows that it's going to pre-process all our data to augment the data set with that standard set of transforms. Now, finally, we're going to call .databunch on this like pipeline that we have here. And this is going to create that image data bunch object that we need to pass into the FastAI model. One more thing we want to do, we want to do that normalization, and we're going to do it using this function called ImageNetStats. So if we do dot normalize ImageNetStats, that's going to tell it to use the normalization from ImageNet. So ImageNet is this massive, massive public data set of hundreds and hundreds of thousands of images that have been classified into, I think it's like 1,000 different classifications, but that entire model is just public. And it was trained, for like hundreds of hours. So this is something that you do all the time with like data science is that you borrow like normalization parameters and things from other models that have been trained on like larger data sets. So FastAI just comes with the default thing called ImageNetStats. And if you normalize with that, it's a lot better than just doing like random normalization and trying to like train from there. So anyway, this is all that we need to create the data in the format that we need to pass into our model. And we can do some stuff to like now look at what we've created. So I can do data dot show batch. And let's say rows equals 3, fig size equals 7 by 7. Yeah, and I'm just going to make some new rows just to make this not on the bottom of the page. But yeah, you can see that if you do data.showBatch, it's going to show you a random sample of your data. And this is just a random transform of one of those images, because remember, we did all this pre-processing to expand our data set, and you can see the labels that we have on it. So we can just keep doing this, and it'll just give us, a random sample of our data just to make sure that the label looks correct. And this is actually like what we want to be training on. We can also make sure that it knows about all the classes if we do data.classes. Yeah, and we'll see that these are the different categories that it wants to classify on, and that was just pulled out of the unique values of the file system names. So now that we have our data in the right format, we're going to need two more things. We're going to need a model architecture and weights. So just to quickly talk about, I guess, what that is. Like, have you ever seen an image of a neural network? It looks kind of like this, right? Like, you got a bunch of neurons here, and then they are all connected to like another row of neurons like this, and then each thing is connected to each thing. And then there's, like another row here, and each thing is connected to each thing there. And like this whole thing, right, is gonna output that array that we want. That is the predictions of, what is the probability that the given input is any of the given brands. And this thing right here is like called the model architecture. So the model architecture is things like how many neurons are in each row, and then how many rows of neurons are there? They call these layers, right? Like how many layers of neurons are there? And what are these activation functions here, right? Like what threshold does the value at this node need to be before it will pass a message on to the next node versus just kill it? Things like that. And then what they call weights, right, or params, like weights or parameters, things like that, are the actual values of each individual node. So each individual node has like a value, and then you're going to pass an image into it, and it's going to go through these activation functions and say, like, if that value is above a certain thing, or I'm going to manipulate in some way and then pass to the next neuron, etc. And then what we're going to do when we train the model is that we are looking at the loss of the entire system. So we're looking, given the entire training data set, and then the predicted outcomes, how wrong are they? And then which nodes are most responsible for being wrong. And then we're going to update those weights until the loss of the entire system is minimized. That is, called backpropagation, when you go back through the system and you find the nodes most responsible for the loss and update the weights. But anyway, the short and long of it is, instead of having to build this architecture and the initial weights, right? Because you can start with just random weights and train the neural network, and you'll eventually get to the right weights, but that's going to take a really long time. So there's a lot of, a lot of research into how you initialize weights in the proper way and things like that. But instead of, coming up with our own architecture and our own parameters to initiate the system with, we can actually just borrow the values from that ImageNet data set, because this is a data set trained to classify hundreds and thousands of images, and it was trained by professionals over a long period of time. So if we just take the architecture of that system, we know that that's a neural network that's very good at classifying images, and we can just start with that and then train it on our data set so that it's just getting slightly more optimized to recognize, images of watches, instead of trying to build all of this from scratch. So the FastAI library comes built in with a link to that to download that ImageNet model and weights, and we're going to just use that. So we use the function to create a new convolutional neural network learner, is something called CNN learner. That's the name of the function. So we want to import that from FastAI Vision. This is actually getting long, so I'm just going to parens this down kind of like this. And I just wanted to do it this way. We could just import this entire library, but I just wanted to make it explicit, like what libraries are coming from that FastAI Vision and which things are like Python standard, like things like that. And we're going to make a new variable called learner. And that learner, and actually we're going to need something in that FastAI Vision library called models also, which is what has access to the models that it knows about. So learner equals CNN learner. And then we're going to pass in 3 parameters to this CNN learner that we're instantiating. So one is the data that we want to train on and validate with. And then the next thing is going to be the model architecture that we want to use. Now, we said there's a default ImageNet trained model that comes with this, and it's in models.resnet34. That's the name of the model. So the architecture of the model is this thing called resnet34, and it's been pre-trained on that ImageNet data set. So we can create a new neural net learner just from our data and that model. And then the third parameter is going to be what output we want to display while we're training it. So I'm just going to do metrics equals error rate and then hit enter. Oh, and error rate's not defined because, again, we need to import it from FastAI Vision. Yeah, so as I hit enter, you can notice that it's downloading that model from PITorch.org. And it's downloading this thing called .pth. So yeah, if we actually look, that's going to download it to cache torque checkpoints resnet.pch. So we can actually take a look at what that's actually downloading. If we did cd.cache, torch, checkpoints. Yeah, and then cat. So I'm just going to let you know this is going to look like gibberish. Yeah. So, I mean, it was worth seeing if that was anything. But anyway, this .pth file is what are going to be pre-trained weights on a neural network model. So it just has like a ton of data. I mean, it was if I actually went back to that cd/.cache, cd torch, cd checkpoints, du-h resnet. Yeah, I mean, it's 84 megabyte file that has all of the pre-trained weights of that ImageNet model. So we can, like if you knew the architecture, this models.resnet34, which is the architecture of the model, and then you had this .pth file, that's all that you need to actually have the pre-trained ImageNet neural network. But anyway, we're going to create this new learner. And then, yeah, if we looked at the type of this, FastAI basic train learner, I guess. Yeah, and then all that you need to run to actually train the model is going to be this function that is learner.fit1cycle. And then the number of epochs that you want to train it on, which I'll say 5. Now, I know that this is like a little bit magical, but like really understanding neural nets is like a whole college, major. So, I mean, there's only like so much you can talk about, I guess. But when you do fit one cycle, it's kind of like a misleading name. You're not only fitting it for one cycle. It's just something that like modulates between different learning rates. So like when I was saying like do the back propagation of the neural network to update the weights on as you're training it, it updates the weights at a fixed velocity, which is called like the learning rate. So if like your learning rate's really high, it's going to update the weights a lot or like a large amount on each cycle. But if your learning rate's really low, it's only going to like tweak the weights a little bit, like tweak the parameters a little bit. But when you do this fit one cycle thing, it actually modulates between a lower and a higher learning rate. And there's reasons for doing this. But yeah, like that's all that it means. It doesn't mean you're only doing it for one cycle. It just means you're modulating it. And then this integer you pass in is the number of epochs you want to do, which will say 5. So I'm just going to hit shift and enter here. And you can see that it's going to output the training loss and validation loss and error rate, which is what we said when we said like we want the metrics to be error rate, is like what we want the output of the CNN learner to be like as we're training it. Now, this is why you want the GPU instances also, because if you ran this function right here on your local machine, it's going to take forever. You're going to have a bad time. I tried it. Even though I'm running this on like an iMac Pro, it still took absolutely forever, like hours and hours and hours to do each cycle, where it's only taking like, a few seconds on the GPU instance. So this is like why you need this cloud instance, right? Like this took 35 seconds. And you can see it gave us on that initial epoch a error rate of 50, which is actually pretty impressive. That only training it for one epoch and already given our validation set, if you passed a random image from our validation set in it, there's a 50% chance that our model would correctly classify the brand of the watch. Just 50% chance after only 35 seconds of training. So now after that next epoch, the error rate is down to 43. So now there's a 57% chance that we would classify an image from the validation set correctly. And remember, the images from the validation set are the images that the model hasn't seen before. So that's already like pretty amazing that only after a minute of training, we're down to 57%. And now the next epoch, look, now we're over 60%. So now given the validation set, our model's over 60% accuracy. And it just keeps getting better and better like as we're doing this. So yeah, I'm going to let this run just to finish it out, and then I'll come right back. Okay, cool. So we finished the 5 epochs, and you can see we got our error rate down to 36%, which means our model was classifying random images from the validation set with 64% accuracy across 13 different brands, which is pretty impressive given that, certain watch brands look pretty similar. So yeah, so now let's see it. Like, there's a couple ways we can just, out of the default FastAI functions, to like kind of dive into this data and take a closer look at it. So I'm going to import another thing called classification interpretation. And then I'm going to make a new interpretation variable. Interpretation equals classification interpretation dot from learner learner. And one of the things that we can do is plot something called a confusion matrix. So let's take a look at that. So like interpretation dot plot confusion matrix. Fig size equals 12 by 12, and I'll do DPI is equal to 60. Yeah, and we'll see what we get this thing called a confusion matrix. And this shows us basically, given each image in our validation set from a certain brand, what did it classify it as? So we could see like with AP, for example, it was really good, where it got like 53 out of, it looks like almost like 60 AP watches, it correctly classified as AP. Whereas, for example, like Omega got 37 Omegas correct, but it classified 11 as Seiko. So like we can see that there's like confusion between Omega and Seiko, which is, interesting, right? Because they do look the same. So that kind of makes sense. We could try to look at like other things like Gucci. It did well here, but it, missed some classifications here, and it missed some with Movado, which makes sense because, right, Gucci and Movado are both kind of like fashion watches that might have, similarities there. So that's kind of cool way to dive into the data. And some of it's like kind of funny, right? Where like you could say like Omegas are more expensive than Seikos, but even our machine learning model says that they look similar, so we could actually like get more into that if we did interpretation.mostconfused. So this is just another way to look at that same kind of chart, but just say what 2 brands did you most confuse? So it says like Zenith and JLC, it confused a lot. Omega and Seiko, it confused a lot. Seiko, Zenith and IWC, things like that. Movado and Gucci, it confused a lot. And like doing things like this are good because it's helping you like understand, like, does this make sense? Like, is this what you would expect? Like if it was confusing AP and Gucci a lot, that wouldn't make sense because those watches look different. So this is just a way to get a sense of like your data, like is this model like relatively right just based on your intuition? We can also look at images of the things that it was the most wrong about. So with each classification, it's going to have a certain confidence that it was right. So it's like, I was very highly confident that this watch was this brand, or I was not that confident it was this brand. But if we look at images that it was very confident about but wrong, that's also another way to like look at the data. So if we did plot top losses, and let's do 9 fig size equals 12 by 12. Yeah, so these are the watches that it was most confused about. So this is what the watch actually was. This is what it predicted. This is what it actually was. And then this is how wrong it was. So like in this example, for example, it was really, really sure that this was an IWC watch, but it's actually a Seiko watch, which makes sense because it has like a tourbillon. It's like kind of confusing to know that that's actually what it was. This one makes sense because, it's a really bad image that like the watch is really short in the box. So like it makes sense that it may not have done well on that. This one makes sense because it predicts that, this is a weird looking watch, things like that. So it's kind of interesting to dive into the data like this where it, was really sure this was an Omega watch. It's actually a Seiko watch again. So interesting ways to look at how your model's doing. Now we can make a prediction too. Like we can use this model now to like predict any random image. So if we look at our data again, here, let me make some more rows just so we're not at the bottom of the page, and do data dot, let's say valid DS, which is the validation data set of 786 items. And let's pick a random one of these, like 109, let's say. Yeah, and this is going to be like the 0th index will be the watch itself, and then the 1 index will be what it actually is. So we can see that this is an AP watch. It has that kind of like hexagonal shape to it. So I would guess that the model would be pretty good at predicting this, and we can actually test that, right, by doing learner.predict. And we want to predict data.validDS 1090, and let's see what it gives us. Yeah, so we could see that it made a prediction, and it predicted that it was AP. And then these are the confidences of each individual index. So it's saying that it's index 0, like tensor 0, just like tensor is just a alias for array. So whatever in like these machine learning libraries they call tensor, you can just think of as an array. That's like a fine way to think about it. So when it says like 0, it just means it's a 0th index in this, which is all the confidences. And remember, if you did like data.classes, that shows you the rows. So it's saying it's index 0 of this, and these are the confidences of it. So it's 98% confident. So this is just scientific notation, but you can make these decimals if you want. But this is saying it's 98% confident that this was an AP watch. And that's a watch that it didn't see when it was training, which is pretty cool, right? Like we just passed in that image and it was really quickly able to identify it correctly. We could do another one. Like let's look at like maybe 108. See what this guy is. And it says that this is a Breitling watch. So let's see how well it does with that. Well, it predicted it was Omega. So it was wrong about that one. But that's, again, a tough one because it's, 107, which is a Rolex. So we can say, how well does it predict this one? And it does predict a Rolex. And it's 92% confident if we look at the value here at index 10, that this is a Rolex. So this model is actually, pretty decent, given that we haven't even trained it that much. So when we want to save the weights that we've trained our model at, we can do learner.save and then some file name. So we'll call this stage 1. And that's going to save that .pth file of the weights that we have trained from our training. Yeah, so in our data folder, it created this folder called models. And in that models folder, it made something called stage1.pth. Remember, those are the weights of our model. So if you could already think like, right, like if we were going to build some application server that had to serve an API where we could query this model, like this .pth file might be useful, or we could load the weights into that application there. Now we can make this model better, right? Because when we were training, so like, remember we had this like architecture that we had the ImageNet pre-trained like architecture and data that we were using. So when we're actually training it, like this model has like a lot of layers to it. And when we were training it, we basically said like we only want to train the layers like towards the end, because the layers at the beginning are normally more general. Like these are just like general pattern recognition, and then at the end is like very, very distinct features. So normally, like if you have a good pre-trained data set, or a pre-trained model, you only want to train the layers at the end. But after you're done training those, you can go back and train the layers at the beginning and actually improve your model. You do want to just be careful that you don't train it too quickly when you do that. So you have to pick a learning rate that's appropriate for like optimizing your model. Okay, so this next thing is like called fine tuning, right? Where you're gonna like retrain the earlier layers of your model. So we want to make sure that the learning rate's not too high when we do that. So we can do learner.lrfind to try and find what we think might be an optimal learning rate to pass in when we train the earlier layers in the model. Yeah, and once this finishes, you can do learner.recorder.plot. Yeah, and this shows you what it expects the loss to be at different learning rates. So we can see like once the learning rate gets like larger here, like it starts to get really bad. So we just want to make sure that like we pass in the learning rate like of this range or something like that, so that our model doesn't go off the rails when we train it. So if you do learner.unfreeze, this is what opens up those earlier layers to training. And then we can do learner.fit1cycle. So we're going to run that exact same thing of 5 epochs, but we want to just make sure that the max learning rate is a slice of 1e negative 4 to 1e negative 2, just so it doesn't go off the rails when we do it. Yeah, and this is called fine tuning, right? When you're going back and you're retraining earlier versions to take a model that's like all right and try to make it like even better. So we're going to let this run and see how it does. Cool. Yeah, and that finished, and you can see it got our error rate down to 22%. So now we're 78% accurate against that validation set, which is awesome. So I wonder now, like, if we were to predict the one that we got wrong, if we would get it right. Let's see. So we knew that this was a Breitling. It didn't predict it correctly last time. And now, right, like using that fine tuning, our model's actually correctly predicting Breitling. And we could learn, I think, like, yeah, so if you do a list, so like we can like look at the actual brand zipped together with this. So this would be the second index of this. And then if we did a list zip data.classes with this, we can actually look at the values that it predicts the confidence of each one. So it was fairly confident that this was a Breitling also. So that's really impressive that doing that kind of fine tuning not just made it predicted accurately, but gave it like a high confidence that it's actually a Breitling watch also. So it seems like our model's much better now than it was before. We can do learner.path, I think shows you the actual path that it's saving stuff to. Yeah, so that's in that chrono analyzer data. And then learner.save, we could say stage 2, but this model's now much better than it was before. Now, if we're looking here, right, we have that stage 2.path file of the weights of our model. But we can actually export the entire model, right? Like the weights, like you only load into a model when you have the specific architecture already. But we want to have just the entire thing as its own package that we can load just in an arbitrary web server environment or application server environment. So I want to do learner.export, which is different than just saving the weights. It's actually saving the entire model. And we're going to call this classifier.pkl. So PKL is like a compressed data format for Python. Yeah, so I wonder if this just saves it to the data environment. So if I did like ls-la grep classifier. Yeah, so when you do export, it doesn't save it in that models directory. It just saves it directly to the path, I guess, of the learner. But this classifier.pickle file is the entire compressed model with the architecture and the weights together. So this is what we're going to actually use to load into our application server when we want to serve an API from this. Let's see how big this is. This is 84 megabytes, right? Yeah, but this classifier.pickle is what has 78% accuracy predicting against our validation set that we could then load into our application server. Yeah, so now I'm going to go back to my desktop. I'm going to CD into that chrono analyzer, which is the local thing we made that had the scraper. And now I'm going to make a directory called, like, let's say, like models, CD models. Yeah, and then I want to download that file from the remote server. So I'm going to do another SCP. But this time I'm just going to put the remote file first. So desktop/keys/machine learning server. And then it's going to be Ubuntu at whatever the IP address of this instance was, which was the 57. I should just have this in my clipboard somewhere. Save me a lot of time. Yeah. And then /home/Ubuntu/ and I don't remember what this is. Yeah, we want /chrono analyzer /data. Chrono analyzer /data, and then /classifier.pkl. And we want to download that to the directory that we're in. Yeah, and then that's downloading the file to my local directory. All right, so once that's done downloading, we could open this in Atom. And we'll see that in our models, we have this classifier.pkl file. Yeah, so our remote server has effectively done its job right now. We have this notebook saved, so we could download this entire notebook if we wanted to. But I think for now, like, we used our GPU server. I'm just going to shut it down now so that I don't continue getting charged with it. So I can stop this server now because we have the .pkl file. That's all that we wanted to get out of it. And now we can make an application server that serves an API from it.